We've been looking at a problem that has two decision-making agents. One of them is a steel plant that has a wastewater treatment problem. There are two types of water, the pickling waste, which is concentrated, and the processed water, which is less concentrated. They can choose to send the pickling waste and the processed water to the wastewater treatment plant, and their wastewater treatment plant will remove 90% of the pollutant, thereby reducing the amount that they have to pay to dispose of the effluent from the wastewater treatment plant by 90%. If they don't treat it, then they have to pay the full strength of the wastewater coming from pickling and process. The government sets a fee based upon the pickling waste, the processed waste concentration, or the treated waste concentration. And the way the government treats it, they have one fee for disposing of pickling waste, which is very high. We'll call that tax pickle. And then they have another fee for what's coming out of the wastewater treatment plant or the processed water plant, because that's lower. We're going to revisit those fees in a second after we look at the interaction between these two players. Suppose that the government wants to decide how they should set their taxes. Remember that whatever is going to come out of the wastewater treatment plant will be reduced by 90%. So there's going to be tax, this is pickle, tax, process, and then there's the fees that they pay for the effluent from the wastewater treatment plant will be tax pickle times 0.1, tax process times 0.1, because the wastewater treatment plant reduces the amount of pollution that will be discharged into the river. The government has to decide then two things, not really three things, because this is constrained by its relationship through this parameter with these fees. The government has to decide the tax on the pickling and the tax on the processed water. And you might ask, how should the government decide? Well, one way to do it is to set it up as a multi-objective decision problem. Suppose we have here the tax on the process, and here the tax on the pickling. Now you could ask yourself, what's the objective going to be? We might choose that the government wants to maximize its tax revenues. And you could say, well, the higher the tax, the more they collect. There's going to be some objective function, which is max z as a function of these two decision variables. And that's going to be positive, you might think, up and to the right. And that's true if it works out that this is a linear problem. If it's a linear problem, then everything looks good for the government raising more money if they increase the taxes. Here's the difficulty. The higher the government taxes go, the less profitable it is to operate the steel plant. To do this sensitivity analysis, the government must choose the level of their taxes. Those appear like parameters to the steel manufacturer. And then they have to anticipate what the steel manufacturer's new optimum is going to be. How is the steel manufacturer going to respond to the way the government sets the price of pollution? We might find, I'm just making this up now, but we might find a value of z that increases in exactly the way our intuition is saying, that at, of course, no taxes, they make no money. But then after they start charging a little bit of tax, either for processed water or for pickling waste, Z1, Z2, it's kind of deceptive. These are the different isoquants of Z, and they increase as we go up and to the right because the government is collecting more money for more taxes. But what happens when the taxes get so high that the steel manufacturer can no longer be profitable at any rate of production, at any treatment levels? The steel manufacturer may choose not to operate at a loss. they might choose to shut down altogether. We don't know what that curve looks like. It's not a constraint per se. The government may set the taxes as high as they like, but suppose that there is some combination of taxes, and on this side of that combination there's no profit for the steelmaker, and on this side there's increasing profit as they go down, as the taxes are reduced. There's no reason for the steel manufacturer to operate without a profit. And so the government, through their understanding of the steel manufacturer's systems model, could anticipate that if they set the taxes too high, the steelmaker goes out of business and everybody loses their job. If they set the taxes too low, then they don't fund their government. They get no revenue. Now, this is an interesting problem for the government to set the tax, and it's a multi-objective problem because it has these two variables, to set the taxes at some optimal level. The way I've drawn this diagram, it's not to scale, and I'm not saying this is a solution, but the way I've drawn this diagram, because of the slope of one line and another, it sure looks like the government optimum would be here at an extreme point. But let's consider something a little bit different. Now we've done the sensitivity analysis, so we understand how the government revenues vary with respect to the two decision variables, and I think that's fascinating. What if the government's objective was not just to maximize their own revenue? What if the government wanted to minimize pollution? They could set the taxes so high that they would drive the steelmaker out of business. What if the government wanted to maximize jobs? They could set the taxes so low that the steel manufacturer would maximize their production and therefore their profit. But let's change this a little bit. Let's say that the government has two objectives. The first one that they want to satisfy is maximize the production in the steelmaker. That is, maximize steel production because they equate that with jobs. After steel production is maximized, they want to do that at the minimum pollutant levels. So they want to set these taxes in such a way that the steel manufacturer is operating at peak capacity and treating as much pollution as they are capable of treating without reducing their peak production. That's one way to do it, and we would use the constraint method. Choose this as the first objective and then change the variables around, keeping this as a constraint so that they can achieve the second objective. If this isn't the objective that you like, we'll call that 2A, you could choose 2B. Only after they maximize jobs, only then would they choose to maximize revenue. Your task is to build the systems model, both for the steel manufacturer and for the government, and to solve these two problems. Figure out which combination of decision variables results in maximum steel production, maximum revenue for the government. That's one choice. Maximum steel production and minimum pollution, or maximum revenue, that is always a choice, or maximum steel production and then maximum revenue. So there are three problems to solve. The first problem, max government revenue, and assume that the steel manufacturer is going to minimize their pollution costs. The second problem, this multi-objective problem, max steel production, which we equate with jobs, and only then min pollutant. And then the third problem, max production and then max revenue. Only after the production is maximized and you're operating at maximum productivity in the plant, only then would you set the taxes as to extract as much money. So you got 3 different problems. And this solution of these problems constitutes a fairly complicated engineering report. I want to see what you come up with.